NASA is suddenly obsessed with Venus again, lining up orbiters and a probe to dive straight into those acid clouds. And the real question is, why this planet? Why now? And what are they so desperate to find out up there? Venus is not some exotic outlier. It is almost a carbon copy of Earth in basic stats. It's about 12,100 kilometers across. Earth is about 12,700. So the size difference is small. The mass is a bit lower, but the surface gravity would feel close to what you feel now, not like the Moon, not like a tiny asteroid, just slightly different. It orbits only about 30% closer to the Sun than Earth does, roughly 108 million kilometers instead of 150 million. On a solar system scale, that is a small shift inward, not a totally different zone. Both planets formed from the same disk of rock, ice, and metal at the same time in the same neighborhood. So here's the basic puzzle. If you start with almost the same size, almost the same mass, pretty similar orbit and probably similar ingredients, why did one world end up with oceans, continents, and life, and the other end up with an atmosphere that can crush a submarine and a surface that can melt metal? That question alone is enough to drag Venus right back to the front of NASA's target list, because if two near twins can split this hard, then our picture of how safe an Earth-like planet really is might be way too optimistic. Now, how bad is Venus actually, if you strip away the drama and just look at the numbers? Down at the surface, the temperature is around 740 Kelvin, that's about 467 degrees Celsius, or roughly 872 degrees Fahrenheit. That is hotter than most industrial ovens, everywhere, all the time, day and night, equator and pole. The atmospheric pressure is about 93 bars, which means 93 times the pressure you feel at the sea level on Earth. In everyday terms, that's what you experience almost 900 meters underwater, close to 3,000 feet down. The atmosphere itself is about 96.5% carbon dioxide, around 3.5% nitrogen, and then trace gases. Oxygen's basically not part of the story, water vapor is almost gone. Lead melts at about 327 degrees Celsius, so in that environment, a solid block of lead would soften and flow. Any lander is dealing with conditions where common metals fail, electronics overheat, and seals and cables break down fast. You can think of the greenhouse effect on Venus as not just strong, but totally off the rails. The system never hit pause. It just kept trapping heat until the whole surface environment was reset into this extreme state. NASA wants to understand that process in hard detail, because the difference between strong greenhouse and runaway greenhouse is exactly the line that tells you how a planet crosses from difficult to live on to impossible to live on. For a long time, the easy story was, Venus is cooked and quiet. It did its volcanic activity ages ago. Now it's basically frozen into a place under those clouds. That made it sound less urgent, but recent work has started to break that story. Scientists went back to the radar data from Magellan, the NASA orbiter that mapped Venus in the early 1990s. Using better processing and new analysis techniques, they found something huge near a volcano called Nix Mons, a gigantic lava tube buried under the surface. We're talking about an underground tunnel roughly 1 kilometer in diameter and at least 375 meters tall, with a roof maybe 150 meters thick. On Earth, our largest lava tubes are only a few tens of meters wide. The Venus structure is on a totally different scale. You only get a tube like that if a lot of lava once flowed there, stayed molten, drained away, and left a hollow. That is the signature of serious volcanic activity. And that's not the only clue. Other Magellan data and later observations hint at changing thermal signatures and surface features that may be tied to ongoing volcanism. When you put it together, Venus starts to look less like a dead fossil and more like an active world that is still moving heat from its interior to its surface. So now the question turns sharper. If Venus is still geologically alive under that thick hot air, what does that mean for how it got this way? And how stable it really is. This is where NASA uses a phrase that sounds dramatic but is meant literally: Venus as a lost habitable world. That phrase is not a sci-fi tagline, it's the working hypothesis. Early in the solar system, the sun was dimmer. Under that softer light, Venus might have cooled enough for water vapour to condense into liquid oceans. If that happened, you could have had shallow seas, clouds, rain cycles, maybe even a stable climate for a while. The planet's size and gravity were right. The basic rock chemistry was right. The only real difference was that extra solar energy. Over time, as the sun brightened and volcanic activity added more carbon dioxide to the atmosphere, the balance could have shifted. Oceans would evaporate faster, water vapour would increase, trapping more heat. As the surface warmed, more CO2 would be released from rocks, again trapping more heat. At some threshold, the system would cross into a state where liquid water could no longer exist on the surface. Once the water is in the atmosphere as vapour, sunlight can break it apart. Hydrogen escapes to space. Oxygen reacts with the surface or gets lost too, and you're left with a dry, dense, carbon dioxide-dominated atmosphere. That is the runaway greenhouse idea in plain language, and Venus is the best possible test case for it. If NASA can measure the atmosphere and surface precisely enough, it can tell whether this scenario really happened, or whether something even more extreme went on. Either way, it's directly relevant to Earth, because it tells you whether a planet like ours has a built-in safety margin, or whether the difference between blue Earth and Venus outcome is smaller than we thought. So if Venus is that important for climate physics and planetary history, why isn't Mars the only focus? Why is NASA pushing Venus back onto the main stage now? From an orbital mechanics perspective, getting a spacecraft from Earth to Venus is not harder than going to Mars, and in many launch windows it actually requires less change in velocity. The trip time is shorter, on the order of a few months. Once the spacecraft arrives at Venus, the thick atmosphere becomes a tool. You can use it to slow down an orbiter by skimming the upper layers, a technique called Aerobraking, which saves a lot of fuel. You can send descent probes that rely mainly on drag and heat shields, not on huge rocket burns to get into the lower atmosphere. The same dense air that makes the surface deadly also makes the mission design more efficient in some ways. On top of that, the science value is concentrated. One planet gives you an extreme greenhouse atmosphere, intense surface conditions, likely active volcanism, and a history that may include oceans and then total water loss. Data from Venus plugs straight into climate models, geology models, and exoplanet models. Mars is great for learning about cold, thin atmospheres and past habitability, but Venus hits the how far can a rocky planet fall question directly. For an agency that is supposed to expand fundamental knowledge, not just chase nice images, Venus is a very strong target. So now you're left with a tougher, more personal question: if we finally study this failed twin properly, and it turns out Venus really did start much closer to Earth and then tip into permanent disaster, what does that say about how safe our own climate path actually is? How is it possible that almost everything you think you know about Venus comes from a spacecraft that finished its job before most people watching this were born? NASA's last dedicated Venus orbiter, Magellan, launched in 1989 and arrived in 1990. His job was simple and brutal: use synthetic aperture radar, or SAR, to see through the permanent cloud cover and map the surface. Over its mission, Magellan imaged more than 98% of Venus at resolutions between about 120 and 300 meters per pixel, and in some products even finer. That was enough to see volcanoes, long lava channels, weird pancake-shaped domes, and a surprisingly young surface. It also mapped the gravity field, giving the first hints about what's going on inside the planet. Then from NASA's side, things went quiet. Magellan ended in the mid-1990s. After that, NASA's attention moved hard to Mars, to Jupiter's icy moons, to asteroids and comets. Other agencies flew Venus missions like ESA's Venus Express and JAXA's Akatsuki, but there was no new NASA radar mapper taking over where Magellan left off. Your mental image of the Venus surface is basically frozen in early 1990s data. In internet terms, that's pre-smartphone, pre-social media, pre-HD anything. So right now, when you think of Venus, you're picturing a planet-sized mystery built out of old radar snapshots that can't show changes over years or decades. If volcanic vents opened, if ground swelled over a magma plume, if cracks slowly widened, Magellan's resolution and cadence were just not enough to track that. And that 30-plus year gap is exactly what the new missions are built to kill. So how do you upgrade from "we have a grainy map" to "we can see the crust flex by centimeters from orbit"? NASA's answer on the orbital side is VERITAS, short for Venus Emissivity, Radioscience, INSAR, Topography and Spectroscopy. It's an orbiter designed to remap the entire planet with modern radar and infrared instruments. The plan is to get global radar images at around 30 meters per pixel, with selected high-interest areas going down to about 15 meters per pixel. That is about an order of magnitude sharper than typical Magellan data. VERITAS carries an interferometric synthetic aperture radar, often called INSAR. Instead of just taking one radar picture, it flies repeated passes over the same region and compares them. Tiny differences in the distance to the ground, down to on the order of a couple of centimeters, show up as phase shifts in the radar signal. The mission is aiming for sensitivity to vertical motions around 1.5 centimeters, less than the thickness of your finger, across an entire planet. On top of that, VERITAS will build a topographic map of Venus with vertical accuracy of a few meters, so you finally get a true 3D model of mountains, rifts and the plains, not just a flat radar brightness map. It will also do gravity science, tracking tiny changes in the spacecraft's velocity as it flies over denser or lighter regions underground, to infer the structure of the interior. Put this together, and you get a very sharp picture of what the surface is doing right now. You can see fresh lava flows that are smoother and less cratered than their surroundings. You can see if certain regions are slowly rising or sinking because of the moving magma. You can test whether Venus has something like plate boundaries, or if the crust moves in blocks, or if it is mostly a single stagnant shell with local fractures. If VERITAS sees real deformation over the mission lifetime, then Venus is geologically dead is finished as an idea. But radar and gravity don't tell you what the atmosphere is made of, or how it got that way. For that, NASA is sending something much more aggressive. Alongside VERITAS, there is DAVINCI, which stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging. This mission is not just an orbiter flyby. The key element is a descent probe, a tough spherical capsule that drops straight through the atmosphere once and dies at the end. The carrier spacecraft releases it a couple of days before arrival, and then the probe slams into the upper atmosphere at around 11 to 12 kilometers per second, more than 40,000 kilometers per hour. Science operations start at about 67 kilometers altitude, roughly 42 miles above the surface. From there down to near ground level, the probe continuously measures temperature, pressure and wind, building a vertical profile of the atmosphere. Instruments like the Venus Mass Spectrometer sample the gases, including noble gases such as argon, neon and xenon, and their isotopes. Another package, focused on structure, tracks how the air density and winds change as the probe falls. Near the bottom, DAVINCI's descent imager looks out through a sapphire window and takes high-resolution pictures of the surface around Alpha Regio, a region of complex highland terrain called Tessera. The goal is sub-meter detail, so you can see boulders, layering and small fractures in a place that may record the oldest crust on Venus. This is a one-shot lab. Once the probe reaches the lower atmosphere, the combination of around 93 bar of pressure and roughly 467 degrees Celsius will kill it, probably within minutes of reaching the surface if it reaches it at all. But in that short window it can return enough data to lock down the composition and structure of the lower atmosphere in a way we've never had before. So then the obvious question is, if VERITAS is already doing radar, gravity and topography, and DAVINCI is doing chemistry and structure, why do you need both? Why not just pick one? The answer is that Venus only makes sense if you connect its interior, its surface, and its atmosphere as one system. VERITAS shows you where the surface is young, where volcanism is active or recent, where rifts and the mountains are growing and how mass is distributed inside the planet. Da Vinci tells you which gases are present, in what ratios, and how temperature and pressure change from the cloud tops down to the deep atmosphere. For example, if VERITAS sees a region that looks freshly resurfaced by lava, and Da Vinci's measurements show certain sulfur gases, or CO2 levels that match active outgassing, you can tie a specific volcanic process to a specific atmospheric signature. Noble gas ratios measured by Da Vinci act like timestamps, telling you how much atmosphere was lost early on and how much came from later volcanism. Those constraints feed back into models of the interior which VERITAS tests with gravity data. You end up with a chain. Core and mantle drive volcanism. Volcanism shapes the crust and releases gases. Those gases build and modify the atmosphere. The atmosphere sets the climate. That's why NASA didn't treat these as competing Venus proposals and kill one. It treated them as a matched pair. One mission sees the solid planet, the other tastes the air. Together, they can finally answer whether Venus really passed through a habitable phase and how it locked into its current state. The real payoff comes when you stop looking at Venus in isolation and line it up next to Earth and Mars as 3 points in one big experiment. Earth, Venus, and Mars are all rocky worlds. Earth and Venus are almost the same size. Mars is smaller, but still big enough to have had volcanism, a thicker past atmosphere, and liquid water on its surface. With VERITAS and Da Vinci, you'll have modern high-precision data on all three. Earth, obviously, Mars from decades of orbiters and rovers, and Venus from the new missions in the 2030s if the current plans survive. Once that data exists, climate and geology models can stop guessing. You can actually run scenarios like, what if you put Earth at Venus's orbit but kept Earth's atmosphere? What if you give Venus Earth's orbit but keep Venus's CO2? What if Mars had a thicker atmosphere maintained by more volcanism? You can test how sensitive climates are to incoming sunlight, to greenhouse gas levels, to the presence or absence of plate tectonics. You can check whether our current habitable zone diagrams are too generous. This is not just about drawing nicer maps, it's about changing the baseline for how long an Earth-like planet can stay habitable, and how easy it is for it to slip into a one-way greenhouse state. And that sets up the next big question you have to face. Once you understand Venus's runaway greenhouse in detail, what does that say about the upper limits of Earth's own climate, and how close we might be over long timescales to paths that don't let you turn back? Why does one planet get a thin, breathable sky, and the other get an atmosphere that is basically pure greenhouse gas with no off switch? Venus is where you find out what happens when the greenhouse effect stops being self-regulating and just keeps ramping up. Its atmosphere is about 96.5% carbon dioxide and roughly 3.5% nitrogen. Everything else is tiny traces. On Earth, people get worried when CO2 goes above about 420 parts per million, which is around 0.042% of the air. On Venus, CO2 is not a trace. It is the air. That means almost every photon of infrared heat coming up from the surface gets a good chance to hit a CO2 molecule, get absorbed and get re-emitted back down again. On Earth, the greenhouse effect is strong but limited because water condenses, carbon gets locked into rocks and oceans, and the atmosphere is mostly nitrogen with just a thin layer of greenhouse gases. On Venus, you are looking at the end state where all those brakes failed. You can't just plug in a stronger version of Earth into a computer model and call it done. The physics changes when the main gas in the atmosphere is the greenhouse gas. That's why NASA cares so much about real measurements. They want to know exactly how CO2 behaves when it is basically 100% of the atmosphere, not just a few hundred parts per million. If the composition is that extreme, what does that actually feel like at ground level? How heavy is that air? Down at the surface, the pressure is about 93 bar, around 93 times Earth's sea level pressure. In everyday comparison, that's like standing 900 meters underwater, close to 3,000 feet deep in the ocean. You're not just dealing with hot air, you are dealing with an ocean of gas sitting on top of you. That pressure is not just a number to throw into a trivia list, It changes how CO2 absorbs and emits heat. It changes how rocks chemically react with the air. It changes how fast volcanic gases dissolve or get scrubbed out. In climate models, there is a set of equations that describe how radiation moves through an atmosphere. Those equations were mostly tested in the 1 bar, mostly nitrogen thin greenhouse regime, because that's what we live in. When you suddenly plug in 93 bar almost all CO2 surface at around 467 degrees Celsius, the behaviour is different. Your absorption lines matter, collision processes between molecules matter more, convection works differently. You cannot safely test that on Earth. You cannot build a full-scale atmosphere experiment at those pressures and temperatures. Venus is the real-world laboratory. You point instruments at it and let nature show you how extreme greenhouse atmospheres actually transport heat. If the surface is that insane, is there any part of Venus that looks even slightly familiar to you? Any layer where conditions line up with what humans are used to? There is one band in the atmosphere that stands out. Around 48 to 50 kilometers above the surface, the pressure drops to around 1 bar, similar to Earth's sea level, and the temperature falls into the range of roughly 30 to 70 degrees Celsius, about 86 to 158 degrees Fahrenheit. That's hot and uncomfortable, but it is not fatal in the same instant way the surface is. This region sits inside the thick cloud deck, which is made of droplets of sulfuric acid solution, not water, but in terms of pressure and basic temperature, it looks surprisingly like a high, warm layer of Earth's sky. Da Vinci's probe will fall straight through this zone. As it passes, it will measure pressure, temperature, winds, and the detailed chemistry of the gases. That gives you a clean vertical slice through a climate system where the lower atmosphere has basically been compressed into a superheated ocean of gas under it. You get to see how energy and chemistry move from that tropics in the clouds layer down into the deep, dense, hot region below. For climate science, that is gold, because you can compare a region that looks a bit like Earth's atmosphere to a region that looks like nothing we've experienced in one continuous profile. But knowing the current layers is only half the story. How do you tell what the atmosphere used to be like, and how much of it has been lost or added over time? This is where noble gases come in, and this is one of the main reasons Da Vinci exists. Noble gases like argon, neon and xenon don't react much chemically. They mostly just sit there and record what has happened to the atmosphere as a whole, by measuring not just how much of each noble gas is present, but also the ratios of different isotopes. You get a kind of timestamp. Some isotopes are produced or removed preferentially by certain processes: volcanic outgassing, radioactive decay, atmospheric escape to space. If Venus lost a lot of water early on, hydrogen from that water would have escaped into space much more easily than heavier atoms. That process leaves a clear mark in the ratio of normal hydrogen to deuterium, a heavier form of hydrogen. Venus's atmosphere is already known to be strongly enriched in deuterium compared to Earth, which is a big hint that huge amounts of water were lost. With Da Vinci, NASA wants to tighten those numbers and add noble gas isotopes on top to separate this part of the atmosphere came from early formation, this part was added by later volcanism, and this chunk was lost to space over time. That is climate archaeology. You're not just staring at it's hot now. You're reconstructing the sequence of steps that took the planet from maybe wet and mild to permanently baked. Once you have that kind of timeline, what does it do to your assumptions about Earth's climate and about Earth-like planets in general? Right now, most of your intuition about climate comes from one data point: Earth. You're used to a thin, mostly nitrogen atmosphere at around 1 bar, average surface temperatures around 15 degrees Celsius, about 288 Kelvin, clouds made of water, and a carbon cycle that has kept things roughly in a habitable range for billions of years. It is easy to think of that as normal for rocky planets. Venus basically stands there and says, no, that's the weird case. It runs the same physics with different boundary conditions and ends up at roughly 740 Kelvin at the surface and 93 bar of pressure, with almost pure CO2 air and no liquid water. When you take general circulation models, the same kind of computer codes used to simulate Earth's climate, and you force them to match Venus data, you stress test every assumption they make. If the models can reproduce Venus's winds, temperature profile, and energy flows under those extreme conditions, then you know the core physics is solid. If they fail badly, you know where the gaps are. Once those models are tuned so they work for both Earth and Venus, you can stop treating Earth as the only valid testbed, and you can run serious what-if scenarios across a wide range of atmospheric pressures and compositions. The conclusion that comes out of that is not comfortable. A planet that is Earth-sized, with rock, a metal core, and roughly the right amount of sunlight, can flip into a runaway greenhouse state and stay locked there for billions of years. Venus is not some temporary spike. It has been in this mode for a very long time. That means there is no built-in guarantee that Earth-like automatically means safe for life forever. The system can cross thresholds that don't easily reverse. Venus is the physical receipt that proves it. So the real tension is this. Once you fully decode Venus's climate history, you're forced to ask a sharper question about your own world. Are we sitting comfortably far away from that kind of runaway? Or are we closer to those tipping points than our Earth-only models have been telling us? You're looking at two planets built from almost the same stuff in almost the same place, and somehow one ends up with blue oceans and breathable air, while the other is a high-pressure CO2 furnace. That mismatch is the core of the Venus problem. When the solar system formed, Earth and Venus pulled in very similar ingredients. Silicate rock for the mantle and crust, metal for the core, and volatile ices like water and carbon-bearing compounds delivered by comets and asteroids. Their sizes are close enough that, on a simple level, you'd expect them to play in the same league. Earth's radius is about 6,371 kilometers, Venus is about 6,052 kilometers, a difference of roughly 5%. Mass is different by only about 20%. If you shrink Earth to a ball 1 meter across, Venus is a 0.95 meter ball sitting right next to it. Surface gravity is similar too, only slightly lower on Venus. So purely from the starting kit point of view, nothing screams, one of these will become hell. The real question is which small differences mattered, and how those differences amplified over billions of years. Why did one world keep liquid water, continents, and a complex carbon cycle, while the other locked almost all of its carbon into the air and seems to have burned through any chance at long-term habitability? That's the divergence NASA is trying to pin down. Is Earth the default outcome, or the lucky exception? If both planets started with similar water and carbon, where did Venus's water go, and how do we know it was probably there in the first place? The key players are hydrogen, oxygen, and sunlight. Water is hydrogen plus oxygen. In an upper atmosphere flooded with ultraviolet light from the sun, water molecules can be broken apart. Hydrogen atoms are light, oxygen is heavier. Light hydrogen escapes to space much more easily than oxygen does, especially on a planet that's closer to the sun and getting hit with more energy. Over long timescales, if you keep breaking water and letting hydrogen leak out, you steadily drain the planet's water inventory. Now add one more detail. Not all hydrogen is exactly the same. There's a heavier version called deuterium. It escapes to space more slowly than normal hydrogen because it has more mass. So if a planet loses a lot of water over time, you expect the hydrogen that's left behind to be enriched in deuterium. That's exactly what we see on Venus. The ratio of deuterium to normal hydrogen in its atmosphere is way higher than on Earth. That's a strong signal that the planet once had much more water, possibly enough for oceans, and lost most of it. Da Vinci is going to sharpen this picture. By measuring hydrogen, deuterium, and several noble gases and their isotopes with high precision on the way down, it can estimate how much water Venus started with, how fast it was lost, and whether that loss happened mostly early during a hot young phase, or slowly over billions of years. You're not just asking, did Venus have water? You're asking, did it have Earth-level oceans? And how long do they last before the climate flipped? If water and atmosphere went down such different paths, what about the solid planet under all that air? Did the interior and crust evolve differently too? On Earth, The outer shell isn't one solid piece. It's broken into plates that slowly move, collide, and dive under each other in subduction zones. That constant recycling of crust drags carbon-rich rocks down into the mantle and brings fresh rock up at mid-ocean ridges. Over hundreds of millions of years, that process helps regulate climate. It's part of why Earth's CO2 levels stay within a range that keeps liquid water stable most of the time. Venus looks like it might play by different rules. There's no clear evidence yet of global plate tectonics like Earth has. Instead, a lot of researchers think Venus is in what's called a stagnant lid regime. That means the outer shell, the lithosphere, acts more like a single, mostly unbroken lid. Heat builds up underneath until it can break through in huge volcanic events, possibly even global resurfacing episodes where large parts of the crust get buried under new lava in geologically short bursts. VERITAS is built to test this directly. With high-resolution radar and topography down to tens of meters, it can look for signs of plate boundaries, subduction-like trenches, and organised rift systems. It can also watch for tiny vertical movements in the surface on the order of centimeters that would signal active deformation. If it finds clean Earth-style plate boundaries, that's one story. If it finds mostly large, one-off volcanic provinces and no plate-like behaviour, that supports the stagnant lid picture. And each scenario has different implications for how carbon moves between the interior, crust and atmosphere. So you've got two almost twin planets, the same basic interior recipe, but probably very different ways of moving heat and carbon. What pushed them onto such different tracks in the first place? One big lever is simply how much sunlight each planet gets. Venus orbits closer to the Sun at about 0.72 astronomical units, while Earth sits at 1 astronomical unit. That works out to roughly twice the solar energy hitting each square meter at the top of Venus's atmosphere compared to Earth's. On its own, that doesn't guarantee disaster, but when you feed that extra energy into a climate system with thickening greenhouse gases and no efficient long-term carbon burial, it can be enough to push the planet past the point where water condenses and stays as liquid ocean. Clouds' rotation rate and atmospheric composition tweak this inner edge of the habitable zone. Slow rotation can change wind patterns and cloud cover. Different kinds of clouds can either reflect more sunlight or trap more heat. A slightly different mix of gases in the early atmosphere can shift whether a planet cools enough to form oceans or stays too warm and lets water stay as vapour until it's lost. Right now, our habitable zone diagrams are drawn using simplified models. Once new Venus data is plugged into more realistic exoplanet models, there's a good chance the safe inner edge moves outward. A lot of worlds that we currently call possibly habitable on paper may end up looking more like Venus than Earth. That leads to the uncomfortable question everyone is thinking but rarely says out loud. Is Earth locked into its current path? Or is there any realistic way for us to go Venus? In the very long term, over billions of years, the sun will slowly brighten. Even with no humans around, that extra energy will eventually push Earth toward a hotter state. Oceans will slowly evaporate, weathering and carbon cycles will shift, and at some point, if the planet survives intact, it will get closer to Venus-like conditions. That is just stellar evolution. The shorter-term concern is how far and how fast human activity can move us along that curve. We are adding CO2 to the atmosphere at a rate the natural systems struggle to absorb. That does not mean Earth will suddenly become Venus in a human lifetime. The two situations are not identical. But Venus shows you, in a very direct way, that a rocky planet with roughly the right size and similar starting ingredients can slide into a state where liquid water is gone, the air is almost pure CO2, and the climate is effectively stuck. NASA's real question at Venus is simple and sharp. Where are the one-way thresholds in a system like this? How much greenhouse gas? How much solar input? How much loss of water do you need before the feedback stops pulling you back toward a stable climate and start locking you into a runaway? Once we know where those thresholds sit for Venus, we can place Earth on that map more honestly. And that immediately raises the stakes for everything else in the story. Because to answer, how close are we to a path we can't reverse? You have to understand not just the surface and the rocks, but the winds, the clouds, and the hyperdense atmosphere that makes Venus so hostile right now. How can a planet that takes 243 Earth days to spin once have an atmosphere that races around it in just about 4 days? Venus's solid body rotates painfully slowly, one full turn in roughly 243 Earth days, and it does it backwards compared to Earth. But up at the cloud tops, around 60 to 70 kilometers above the surface, the atmosphere is in constant overdrive. Winds there reach around 100 meters per second, roughly 360 kilometers per hour, about 220 miles per hour. The entire cloud layer circles the planet in about 4 Earth days. The ground crawls, the atmosphere sprints. That state is called superrotation. This is not a small detail. It means the atmosphere is almost decoupled from the planet below. Something in the way heat from the sun, planetary rotation and friction all balance out has produced a circulation pattern that our current models don't fully reproduce without a lot of tuning. NASA wants to know what that something is, because a lot of exoplanets, especially ones that are tidally locked with one side always facing their star, are expected to develop the same kind of superrotation. If you don't understand it on Venus, you're guessing when you try to simulate those worlds. So the next question is, what exactly are those fast-moving clouds made of, and why does that matter for climate? Those bright Venus clouds are not water clouds like the ones you see on Earth. They are made of droplets of concentrated sulfuric acid solution, roughly 75% acid, the rest mostly water. That's not just extra poisonous, it changes the physics. Sulfuric acid droplets absorb and reflect sunlight differently than water droplets. They interact with infrared radiation differently. They set up a different balance of heating and cooling in the atmosphere. The sulfur in those clouds likely comes mainly from volcanic outgassing, gases like sulfur dioxide pushed up from the interior. In the upper atmosphere, sunlight and chemical reactions turn some of that into sulfuric acid, which condenses into droplets and forms the thick cloud decks we see. So the clouds are not just decoration, they're a direct link between the interior and the climate system. Da Vinci will pass through those cloud layers and measure the vertical structure of the chemistry in detail. How much sulfur dioxide at each altitude, how concentrated the acid droplets are, what other trace gases are mixed in. At the same time, missions like VERITAS will be checking the surface and interior for signs of ongoing volcanism that could be feeding fresh sulfur into the air. NASA's goal is not simply catalogue weird clouds, it is to build a climate model where sulfur chemistry is treated as a main driver, the same way water is treated on Earth. That leads to a more controversial point people keep coming back to. If there is a layer in the clouds where pressure and temperature are similar to Earth, what are the chances that any kind of life could exist there? At about 48 to 50 kilometers altitude, pressure sits near 1 bar and temperatures are in the 30 to 70 degrees Celsius range, about 86 to 158 degrees Fahrenheit. Those numbers are not too far from some extreme environments on Earth. The problem is the chemistry. The droplets are sulfuric acid, the air is mostly CO2, water is scarce, and the pH is extremely low. Still on Earth, we do see extremophile microbes that tolerate very acidic conditions and high temperatures, as long as there is liquid water and energy sources. That has led some researchers to suggest that, in principle, if Venus ever had life when it was cooler and wetter, some form of it might have retreated into this temperate cloud band as the surface became uninhabitable. NASA is not sending Da Vinci as a life detection mission. The instruments are not built to say yes, this is life, or no, this is life. They are built to measure gases and particles and get the chemistry right. But here's the key point. Once you have high precision profiles of all the trace gases, their vertical distribution, and their time variation, you can check whether everything fits with known photochemistry and volcanism. If something looks badly out of equilibrium, in a way we cannot explain with non-biological processes, then the life question becomes serious. Even if the answer is no, it's all abiotic, that still matters, because it defines what a lifeless but complex sulfuric atmosphere looks like. All of this feeds back into one big technical challenge. Can our climate models, the same kind of general circulation models we use for Earth, actually handle a 93-bar sulfur cloud super-rotating atmosphere. Right now, the same families of models that do a good job reproducing Earth's jet streams and storm tracks often struggle with Venus. They can produce super-rotation, but it tends to be weaker or less stable than what we see, unless you tweak parameters or add extra processes. That gap tells you there is something missing or not fully captured in the physics. Maybe small-scale waves transporting momentum, maybe the way clouds and radiation interact, maybe friction with the lower atmosphere. With DaVinci's detailed vertical profiles of temperature, pressure and winds, plus long-term cloud tracking and thermal data from orbiters, modelers will be able to test their codes under truly extreme conditions. If a model can match Venus's circulation with 96.5% CO2, dense sulfuric clouds and fast superrotation, then you can be more confident when it predicts changes in a 1-bar, mostly nitrogen atmosphere like Earth's. If it fails, you know exactly where to improve it. Venus becomes a stress test for climate physics. Even beyond winds and clouds, there are still open questions about basic weather and energy flow on Venus that are surprisingly hard to answer from current data. One question is lightning. Some missions have reported signals that look like electromagnetic bursts from lightning, and there are optical flashes that might be related. But the evidence is not clean enough yet to say how frequent it is, how strong it is, or exactly where in the atmosphere it happens. Lightning in a dense CO2 atmosphere with sulfuric acid clouds is not just a curiosity. It would affect chemistry, possibly generating reactive species that change how gases cycle. Another question is how the night side of Venus cools. On Earth, our thin atmosphere and fast rotation mean the night side cools off significantly, and heat is constantly being moved around. On Venus, with 93 bars of CO2, the lower atmosphere stores and transports huge amounts of heat and the planet rotates very slowly. The way the night side radiates heat to space, especially from different altitudes, still isn't mapped in enough detail. NASA wants better vertical profiles from DaVinci and better thermal maps from orbiting missions to close that energy budget. When you know exactly how much energy is coming in from the sun, how much is absorbed at each layer, how much is moved around by winds, and how much is emitted back to space, you have a full accounting of an extreme greenhouse atmosphere. Once you can do that for Venus, you can apply the same methods to hot exoplanets with thick atmospheres and strong stellar irradiation. And that ratchets the tension up again, because the more clearly you see how a planet like Venus moves heat, drives winds, and balances its energy, the harder it is to pretend that Earth's milder climate is guaranteed to stay mild under all possible conditions. Venus doesn't just have a few volcanoes, it is coated in them. And that tells you straight away this planet has moved an insane amount of magma in its history. Magellan's radar maps showed thousands of volcanic structures across Venus, from wide-shield volcanoes to domes, pancake-shaped flows, coronae, and huge lava plains. Some lava channels run for thousands of kilometers, longer than the biggest rivers on Earth, just made of frozen rock instead of water. You don't get that kind of landscape from a quiet interior. Even if all of that activity happened in the past, it means Venus's mantle has been very good at melting rock and pushing it to the surface. The unresolved question is simple and sharp: is that chapter over? Or is Venus still doing this right now? VERITAS is built to answer that, with radar about 10 times sharper than Magellan and the ability to measure tiny vertical shifts of the ground. It can tell whether volcanoes are just fossils or active plumbing systems that are still refilling, inflating and erupting. If you see new flows or domes gently rising over a few years, you know the planet isn't done yet. One recent clue already points in the still active direction, and it came from going back to data we already had and processing it properly with modern tools. Reanalysis of Magellan radar around the volcano Nix Mons revealed a gigantic lava tube under the surface, basically a cavern carved out by flowing lava, and then left hollow after the flow drained away. The structure is about 1 kilometer across and at least 375 meters tall, with an estimated roof thickness of around 150 meters. On Earth, the largest known lava tubes are a few tens of meters wide. This Venus tube makes them look tiny. A tube like this likely runs for many kilometers, maybe longer, depending on the flow that created it. A void that size doesn't form in a small local trickle of lava. It requires long-lived, high-volume flows, the kind of volcanic behavior you associate with a very active mantle and sustained eruptions. It also suggests that Venus's crust can support large underground cavities at high temperature and pressure. VERITAS and European missions like Envision will be able to hunt for more features like this, at much higher resolution, and map out how common they are. For future robotic missions, those tubes are also interesting as potential underground shelters from the brutal surface environment, at least in a far future scenario with landers or long-lived hardware placed down there. But the lava tube is just one piece. The whole face of Venus looks young, and that's weird for a planet that's been around as long as Earth. Counting impact craters is one of the standard ways to estimate surface age. More craters generally means older terrain. Venus has relatively few craters, and they're distributed in a way that suggests a lot of the surface was reset in a geologically short period, maybe a few 100 million years ago. That's young compared to the 4.5 billion year age of the solar system. The simplest interpretation is that huge eruptions, or even planet-wide resurfacing events, buried older landscapes under fresh lava. VERITAS will refine this picture with better crater statistics, better topography, and gravity data that can reveal mantle plumes and hot upwellings under the crust. If it finds that resurfacing is still happening in patches, or that it operates on some kind of rough schedule, that means Venus has a global heat release mechanism we don't see on Earth. Not slow plate tectonics, but massive volcanic resets. That would change how we think about how rocky planets cool and evolve over billions of years. There's also a type of terrain on Venus that doesn't look like much else in the solar system, and DaVinci is heading straight toward it. DaVinci's descent target is Alpha Regio, a region of Tessera terrain. Tesserae are highly deformed highlands, with intersecting ridges and grooves, almost like the crust has been folded, crumpled, and sheared in multiple directions. They may be older than the surrounding lava plains, which means they could preserve the earliest history of Venus's crust. The big question is what they're made of and how they formed. If Tesserae turn out to be made of rock that looks more like Earth's continental crust, silica-rich, lighter, formed in ways that might involve water and recycling, then you have a hint that Venus may once have had processes similar to plate tectonics, at least locally. If there was just another flavour of basaltic volcanic terrain, formed under completely dry, stagnant conditions, then Venus's crust story is very different from Earth's. As DaVinci dives through the atmosphere toward Alpha Regio, it will grab images with resolutions down to sub-meter scales, sharp enough to see individual boulders, layering and small fractures. Combined with the atmospheric measurements along the way, you can connect rock type, deformation style and local chemistry. That's how you figure out whether these highlands are relics of a more Earth-like past or something entirely alien. All of this feeds back into the live question that won't go away. Is Venus erupting now, today in our era? Past missions have already seen hints. ESA's Venus Express reported time-variable thermal emissions in some regions and changes in sulfur dioxide levels in the upper atmosphere that could be tied to recent eruptions. Those signals weren't definitive, but they were enough to raise eyebrows. If fresh lava is still coming out, it would be hotter and have different emissivity, basically a different infrared glow, than older weathered surfaces. VERITAS carries both radar and an infrared emissivity mapper. That combination is powerful. Radar tells you surface roughness and structure. Infrared emissivity tells you about temperature and rock type. Over a multi-year mission, VERITAS can take repeated looks at the same volcanoes, rifts and plains. If a new flow appears, if a dome inflates because magma is rising underneath, or if part of a volcano collapses, the instrument should catch it. The sensitivity down to centimetre-level surface deformation means even slow changes are detectable. If the answer comes back yes, Venus is erupting right now, then scientists suddenly have a live, nearby lab for studying volcanism under conditions totally unlike Earth. Around 460 degrees Celsius, more than 90 bar of pressure, and a dense CO2 atmosphere loaded with sulfur. There is no way to reproduce that whole environment at scale in any lab on Earth. You can test individual materials in ovens and pressure vessels, but you cannot run a full planet. Venus gives you the full system for free if you're willing to fly hardware into it. And once you link active volcanism to changes in the atmosphere, fresh sulfur dioxide, adjustments in temperature profiles, you're no longer just studying a hot rock. You're watching a climate engine run in real time, driven by an interior that refuses to shut down. That pulls the story into the next layer of mystery, because if the interior, the crust, and the atmosphere are all still exchanging heat and gases, the real question becomes how deep the differences between Earth and Venus go. Is it just surface conditions, or is the entire interior system wired differently in a way that decides whether a planet gets a protective magnetic field, stable crust, and a forgiving atmosphere, or ends up exposed under 93 bar of air with no shield at all? How do you judge a planet's entire life story when you can't see a single rock directly, and you're staring through 93 bar of CO2? Venus is Earth-sized, but we still don't know the basic thing you'd like to know about any rocky world. What state is the core in? Fully liquid, partly solid, weird layers in between. How fast is it convecting? Is it even moving much at all? Those details drive everything from magnetic fields to volcanism. We can't put seismometers on Venus yet, so VERITAS has to do seismology the indirect way, by mapping gravity and topography together. Tiny variations in the planet's gravity field tell you where mass is concentrated or missing, and when you combine that with a precise 3D shape of the surface, you can back out how dense the mantle is, how thick the crust is, and what kind of core best fits the data. That's not just trivia for planetary geeks. Magnetic dynamos and plate tectonics both depend on how heat moves out of the core and mantle. If the core is fully liquid and vigorously convecting, you're more likely to get a magnetic field. If it's partly solidified or convecting weakly, maybe the dynamo dies. VERITAS's gravity maps are one of the few tools we have to push on that question for Venus right now. The more tightly we can lock down the interior structure, the closer we get to answering why one Earth-sized planet ended up with moving plates and a strong field, and the other ended up with neither. So then you hit the next obvious problem. What happens to a planet's atmosphere when there is no global magnetic shield between it and the solar wind? Earth has a strong magnetic field that carves out a protective bubble in the solar wind. Charged particles mostly get deflected, guided into the poles, or kept at a distance. Venus does not have that. There is no global magnetosphere generated by a spinning, convecting core. Instead, the solar wind slams directly into its upper atmosphere, and the planet has to rely only on its thick air and induced currents to stand up to that flow. Spacecraft observations already show that hydrogen is streaming away from the planet along its wake. That's one of the ways we know Venus has been losing water. Without a proper magnetic field, light elements like hydrogen escape more easily, which accelerates water loss and helps lock in the dry, CO2-dominated date. The question is whether Venus ever had a dynamo earlier in its history, and then lost it as the core cooled differently from Earth's, or whether its core configuration never favoured a strong field in the first place. Better constraints on core size, density, and heat flow from gravity and topography data feeds straight back into that question. And once you know how easy it is for an Earth-sized world to lose its field, you can say something meaningful about how common magnetically shielded, life-friendly planets might be around other stars. If the interior is still a mystery, can we at least read how strong the outer shell is just by looking at the shape of the surface? Topography is a direct clue to crust thickness and strength. If you see very tall mountains that stay standing over long time scales without collapsing or flowing sideways, that tells you the lithosphere, the stiff outer layer of rock, is strong and probably relatively thick and cool. If instead loads sag and flatten easily, the lithosphere is weaker or hotter. VERITAS is designed to measure Venus's topography with vertical accuracy on the order of 5 meters over global scales, which is a massive upgrade over Magellan. That precision turns the planet's shape into a kind of seismology by proxy. By comparing mountain heights, plateau shapes, and basin depths with gravity anomalies, You can estimate how thick the crust must be under each region, and how rigid it is. It's like watching how a mattress deforms under different weights to figure out how soft or firm it is. Only here the mattress is the lithosphere, and the weights are volcanic plateaus and mountain belts. If certain regions are held up by thick roots of buoyant crust, that suggests long-lived continent-like structures. If everything looks thin and easily bent, that supports a more uniform, stagnant lid. But gravity doesn't just tell you about static support. It can also reveal what's happening in the mantle right now. As VERITAS orbits, it will track tiny changes in its own motion caused by variations in Venus's gravity. Denser regions in the mantle, like hot upwelling plumes or solidified intrusions, pull a bit harder on the spacecraft. Less dense, more buoyant regions pull less. When you map those variations across the globe, you get a picture of where the mantle is rising, where it's sinking, and how that ties into volcanoes and rifts on the surface. It's the planetary equivalent of a CT scan. On Earth, we already have gravity maps that show mantle plumes under places like Hawaii and Iceland. Doing the same kind of mapping on Venus lets you compare convection patterns in two Earth-sized planets with very different surface conditions and tectonic styles. If Venus has strong plumes under its big volcanic provinces, that supports the idea that it's losing heat mainly through localized blowtorches rather than smooth plate recycling. That difference matters for how long a planet can stay geologically active and how its atmosphere evolves. All of this loops back to the thing that makes Venus so terrifying as a climate case: the feedback between the interior, the crust, and the atmosphere. Every time lava erupts, it brings gases from the interior to the surface, especially CO2 and sulfur compounds. Those gases thicken the atmosphere and change how it traps heat. On Earth, weathering and plate tectonics pull CO2 back out of the air and lock it into rocks. On Venus, with extreme temperatures and probably no efficient plate recycling, that balance clearly went wildly toward outgassing. The result is the 96.5% CO2 atmosphere and a 93 bar surface pressure you're dealing with now. By tying together VERITAS's view of mantle plumes and heat flow with Da Vinci's detailed chemistry, how much CO2, how much sulfur dioxide, how the noble gas ratios look, NASA wants to actually quantify that loop. How much CO2 does a certain style of volcanism add over a given time? How does that change surface temperature, which then feeds back into how rocks weather or don't weather? Once those relationships are nailed down for Venus, you can write them as real equations and climate models for rocky planets. That's the bigger picture. You're not just solving a Venus puzzle for its own sake. You're building the physics that decides whether a rocky world ends up with a stable, self-correcting climate like Earth, or tips into a runaway regime where outgassing winds, the sky thickens, and the surface becomes permanently hostile. And the more clearly you can see what's hiding under those 93 bar of air on Venus, the more honestly you can talk about how close other Earth-sized planets might be to the same fate. How do you study thousands of distant Earth-sized planets when most of them are actually more like Venus on steroids? Right now, space telescopes are turning up a huge number of rocky or near-rocky worlds, with sizes from about 0.8 to 2 times Earth's radius, packed close to their stars. Many of those planets get way more stellar energy than we do, sometimes several times more. That is exactly the regime where you expect thick atmospheres, strong greenhouse effects, and possibly permanent cloud decks. In other words, super Venuses, not second Earths. The problem is, we only have one real Venus in our own system, and our data on it is still incomplete. Every precise number Da Vinci and VERITAS pull out of Venus's atmosphere and interior, temperature at each altitude, pressure profiles, gas composition, cloud particle sizes, drops straight into the models we use for those exoplanets. Instead of guessing what a 700 Kelvin high-pressure CO2 atmosphere looks like from far away, you can point at Venus and say, it looks like this, and here's the spectrum to prove it. So distant hot worlds might look like Venus. How do we actually read their atmospheres from light years away? When we observe exoplanets, we don't see continents or clouds directly. We get spectra, basically brightness as a function of wavelength, either when the planet passes in front of its star or when we separate its light from the stars. Certain gases absorb light at specific wavelengths. Water vapour, CO2, methane, sulfur compounds all leave their own fingerprints in that spectrum. Venus's atmosphere is dominated by CO2 and covered in sulfuric acid clouds. That combination produces a very specific set of absorption and emission features. The clouds reflect strongly invisible light, absorb in ultraviolet, and the CO2 bands dominate in the infrared. If you don't understand that pattern for Venus, you can easily misinterpret a similar pattern from an exoplanet as something else, like this planet might be cloudy but mild, when in reality it could be a high-pressure, high-temperature nightmare. NASA is literally using Venus as a calibration target for hot Earth and super-Venus exoplanets. Once you know exactly how a known Venus looks at every wavelength, from ultraviolet through infrared, you can train telescopes like JWST and future missions to spot Venus analogues in other systems and not confuse them with genuinely habitable worlds. That raises the next key question. From a distance, can you tell the difference between a planet that's just hot and one that's in a full runaway greenhouse state like Venus? If all you had was a single temperature number, you'd be stuck, but spectra carry more information than just hot or cold. A runaway greenhouse atmosphere like Venus's has certain traits: extremely strong CO2 features, very little water vapour left in the upper atmosphere, a temperature profile that doesn't cool with altitude the way Earth's does, and a strong thick cloud deck blocking certain bands. A dense but non-runaway atmosphere might have more water, different temperature gradients, and different cloud behaviour. By nailing down the exact spectral shape of Venus's atmosphere, including how it changes between the day side and the night side, and from top to bottom, you get a template for what a runaway greenhouse really looks like from far away. Then when you look at thousands of exoplanet spectra, you can do fast triage. This one looks more like Earth-type conditions. This one is clearly Venus-like. This one is somewhere in between. You don't have to send probes. You can sort worlds by climate state just from photons. That multiplies the scientific value of every exoplanet observation. But climate isn't just about composition and temperature, it's also about how the atmosphere moves, and here, Venus connects directly to another big exoplanet problem: tidally locked worlds. Many close-in exoplanets are probably tidally locked, one side always facing the star, the other always in darkness. Basic physics says their atmospheres should try to move heat from the day side to the night side. But exactly how they do that is hard to simulate. One common outcome in models is superrotation, fast global wind patterns that blow around the planet much faster than the planet turns, just like Venus's cloud tops racing around in about 4 Earth days, while the solid planet takes 243 days to rotate once. If your climate models can reproduce Venus's extreme superrotation using realistic physics, not just tuned parameters, that's a strong sign they're capturing the right processes: wave transport, turbulence, cloud radiation feedbacks. Once that works, you can apply the same models to tidally locked exoplanets with more confidence. If instead your model fails badly on Venus, that failure is a warning sign. Whatever it predicts for those exoplanets is on shaky ground. Again, Venus is the testbed. Put all of this together and you see why NASA talks about Venus as more than just our hot neighbour. The real goal is to turn one extremely hostile planet into a universal template. You study Venus's atmosphere, interior, volcanism and climate feedbacks in as much detail as you possibly can. Then you plug that into exoplanet models and see how many of the Earth-sized planets we've already detected actually fall into the Venus camp, not the Earth camp. You refine which spectral features scream runaway greenhouse, which features hint at thick but non-runaway atmospheres, and which combinations might mean genuinely habitable conditions. Venus stops being a side character you mention after Mars, and becomes the Rosetta Stone for a whole category of worlds: super Venuses, hot Earths, inner-edge planets that sit right on the line between might-keep oceans and lost them long ago. And the more clearly you can read that one stone, the more honestly you can sort the thousands of planets we will never visit into the ones that might host life and the ones that are already locked into a Venus-style fate. Which drops you right into the next practical problem. If all this depends on hard data from inside that atmosphere, how do you actually build a probe that can slam into Venus at more than 11 kilometers per second, survive the entry heating, then fall through acid clouds and crushing pressure long enough to send back the numbers that decide which worlds are dead and which might still be alive? Hitting Venus is not gentle at any stage. From the first contact with the atmosphere to the last meter above the rocks, everything is trying to kill the probe at once. To even start the descent, Da Vinci's capsule slams into the top of Venus's atmosphere at around 11 to 12 kilometers per second, more than 40,000 kilometers per hour, about 25,000 miles per hour. A fast racehorse tops out near 70 kilometers per hour, about 45 miles per hour, so you're coming in more than 500 times faster than that. At those speeds, the air in front of the heat shield is compressed so hard it turns into plasma, and the outer surface of the shield is getting hit with heating rates that would tear apart most materials in seconds. The thermal protection system has to do two contradictory jobs. It has to survive the peak heating long enough to slow the probe, and it has to absorb and shed that energy in a controlled way, so the inside stays cool enough for the electronics. Once the worst heating is over, the capsule is still heading into an environment that climbs toward around 467 degrees Celsius at the surface. So you're designing a shield that sees a brutal short pulse of thousands of degrees on the outside and then a long soak in an oven. Entry, descent and landing on Mars at least give the hardware a cold surface waiting underneath. On Venus, the trial never really ends, it just changes form. Da Vinci's entry profile is a stress test for every high-temperature material and heat shielder concept we've developed so far. And if it works there, it will almost certainly work anywhere else in the solar system. Once you get past the initial fireball, the atmosphere stops trying to burn you and starts trying to crush you, and that drives the entire shape and structure of the probe. A Venus descent sphere is basically a small, extremely tough submarine, except the water is super hot, super dense CO2 and nitrogen. At the surface, the pressure is more than 90 bar, similar to being almost 900 meters, about 3,000 feet underwater on Earth. The shell has to carry that load from every direction continuously with no weak points. Any flaw in a weld or a seal is a guaranteed failure point. On the way down, the probe also has to push through clouds and haze that contain sulfuric acid droplets, so whatever covers the shell, the parachute lines, and any exposed structures has to resist corrosion as well as pressure and heat. The mass budget is brutal. If you add another millimeter of titanium or steel to give yourself a safety margin, you pay for it by removing instruments, batteries, or data systems. There is no infinite mass to play with. The launch vehicle and transfer stage set hard limits. That's one reason Venus descent missions are rare. Each one is a tightly balanced trade between survival time and science payload. You can't afford to waste any kilograms on comfort. Every gram has to contribute to making it to the critical altitudes and taking the right measurements before the environment wins. And during all of that, the probe doesn't just fall silently. Every second of descent has to be turned into data. Da Vinci starts serious science around 67 kilometers altitude, where the air is still relatively cool and thin by Venus standards. From there down to near the surface, the sphere is reading out temperature, pressure, and density continuously, and using accelerometers to infer winds, while its mass spectrometer samples the atmospheric composition, layer by layer. It's like dropping a weather balloon and a chemistry lab tied together, but instead of starting in a calm, cool troposphere and rising into thin air, you start in a comfortable upper atmosphere and sink through increasing heat and pressure until you're effectively inside a blast furnace. Every kilometre of that profile fills in another piece of the climate puzzle. You see where the main cloud decks sit, how thick they are, where sulfur dioxide drops or spikes, where trace gases appear or vanish, how the lapse rate, the rate at which temperature changes with height, behaves in different layers. For climate models, these are not just nice-to-have numbers, they are hard constraints. Instead of tuning a model until it kind of looks right, you force it to match real vertical profiles in a 93 bar greenhouse atmosphere. As the probe gets lower, the focus shifts from the air to the ground, and you get a short, intense burst of pure geology. In the final stages of descent toward Alpha Regio, Da Vinci's camera looks out through a tough transparent window, likely made of something like sapphire, and starts taking high-resolution images of the Tessera highlands. Sub-meter resolution means you're not just seeing broad shapes, you can actually pick out boulders the size of cars, layers in rock outcrops, small faults and fractures. That is a completely different kind of information from radar. Radar can tell you about surface roughness and large-scale structure, but it doesn't show the texture of individual rocks. Even if the probe only survives a few minutes near the surface, those last images are a jackpot. They tell you whether the Tessera rocks look blocky and fractured like old strong crust, whether there are signs of layering that might indicate complex formation histories, whether the terrain is full of loose debris or more solid outcrop. Combined with the atmospheric data from just above the surface, you can link rock type, weathering state, and local chemistry. That's more insight into Venusian geology than decades of remote sensing could ever give alone. All of this depends on one more piece of engineering that Venus both helps and punishes at the same time, using the atmosphere itself as your main braking system. On Mars, the air is so thin that parachutes struggle and you need rockets or clever systems like sky cranes to slow down at the end. On Venus, the air is so dense that simple drag does a huge amount of work for you. A well-shaped capsule can dump most of its kinetic energy into the atmosphere during the high-speed entry, and then a parachute or drag device can take over at lower altitudes to control the descent rate. You don't need massive rocket burns to land softly. The atmosphere will slow you whether you want it to or not. The flip side is that the same dense atmosphere that helps you stop also pushes brutal aerodynamic loads and heating onto the vehicle. The timing of when you deploy a parachute, when you cut it loose, how you angle the capsule, all of that is an orbital mechanics and aerodynamics puzzle. Get the angle wrong and you overload the heat shield. Deploy the parachute at the wrong speed or altitude and you rip it apart, or you end up descending too slowly and cook longer than your thermal design allows. Solving that puzzle for Da Vinci doesn't just buy you one successful Venus mission. It gives you validated entry and descent strategies for any future spacecraft that has to deal with thick atmospheres under strong gravity, from Venus airships to probes at giant planets' moons with dense air. Every second the probe stays alive and transmitting is a direct upgrade to our ability to drop hardware safely into the most hostile environments we know, and that feeds straight into the next problem. Because once you've proven you can fall through acid clouds and 90+ bar of pressure and still send home data, the logical question becomes, how do you see the surface of a world that never ever lets you look down with normal cameras? And how do you track that surface for tiny changes that reveal a live, shifting planet under all that cloud? You can point the best normal camera in the solar system at Venus, and you will still see nothing but a bright, flat sheet of cloud. Those clouds are so thick and so reflective that visible light just bounces off the tops. No ocean glint, no continents, no craters, nothing. That's why when NASA wanted a real map of the surface, Magellan didn't even bother with optical cameras. It used synthetic aperture radar instead. Radar sends out radio waves, listens for the echoes, and builds an image from how strong and how delayed those echoes are. Clouds barely matter to those wavelengths. What matters is surface roughness and the electrical properties of the rocks. Magellan's SAR system mapped about 70 to 98% of the surface, depending on how you count the coverage, at roughly 120 to 300 meters per pixel. That was a huge step. Suddenly you could see volcanoes, long lava channels, fracture belts, impact craters, and weird circular structures all over the planet. But at that resolution, each pixel covers a city block or more. You get the big story, you don't get the small changes. You cannot easily say whether a fault moved a bit or whether a lava flow advanced a few hundred meters between passes. For that, you need a serious jump in sharpness. That's exactly what VERITAS is supposed to deliver. The main radar on VERITAS, often called VOISAR, is designed to push global imaging down to around 30 meters per pixel, with special areas of interest imaged at about 15 meters per pixel. At 30 meters, A single pixel is smaller than a typical sports field. You're no longer just seeing this is a lava plain, you're resolving individual flow lobes, narrow channels, small faults, and subtle landslides. You can see whether a material has slumped off a crater rim, whether a lava tube roof has partially collapsed, whether a rift is cutting through older terrain in a clean line. That level of detail gives you a baseline. Once you have repeated images of the same region, taken months or years apart, you can start looking for differences, not just structure. New bright patches might be fresh flows. A change in radar texture might mean rock has fractured or slumped. You can only do that kind of change detection if your first map is sharpened enough to see the small stuff. But VERITAS doesn't stop at 2D images. The real power comes when you use radar interferometry to build 3D topography and track tiny vertical motions over time. By flying repeated passes over the same ground and comparing the phase of the returning radar signal, VERITAS can detect height changes on the order of about 1.5 centimeters. That is less than the height of a typical smartphone, under an inch, on a planet that ranges from roughly 40 million to over 260 million kilometers away from Earth, depending on the orbits. That precision is extreme. If a volcanic dome slowly inflates because magma is pooling underneath, the surface might rise by a few centimeters over a year. If a rift is pulling apart, the edges might drop or rise slightly. If a region above a mantle plume is very slowly swelling, the whole area could shift upward by small amounts. Interferometric radar sees all of that. It's basically time-lapse vertical motion tracking for an entire planet. For Venus, where we want to know if the interior is still pushing hard on the crust, that is exactly what you want. Then there's the question of what the rocks themselves are, not just where they sit and how they move. For that, VERITAS adds another tool, an emissivity mapper, working in near-infrared windows where Venus's atmosphere is just transparent enough to let some surface radiation leak out. Different rock types radiate heat differently in those infrared bands. Basalt, which is common in lava plains, has one pattern. More silica-rich rocks, similar to Earth's continental crust, have another. By measuring the thermal emission in specific wavelengths and combining that with radar reflectivity, how bright or dark the surface appears in radar, you can start labeling units. This region looks like basaltic lava plain. That region has a signature more consistent with older, possibly thicker, silica-rich crust. This patch might be fresh volcanic material still cooling. That combination is crucial around features like Tessera highlands and big volcanic provinces. If a Tessera region looks more like continental crust, that hints at complex, possibly water-influenced formation processes in the past. If it all looks basaltic, the story is different. If an area around a volcano shows emissivity consistent with hot, new flows, you have a candidate active site. Without the emissivity data, radar images alone can't tell you the full story. All of this radar work on Venus is not just about Venus. It's also training for other worlds with hidden or complex surfaces. The same techniques, SAR imaging, interferometry, emissivity mapping, are exactly what you want for places like Europa and Ganymede, where future missions will use radar to look through ice shells and map subsurface structures. They're also what you use to interpret radar reflections from Titan's lakes and dunes. Venus is a perfect stress test for this technology. Thick atmosphere, weird surface interactions, lots of opportunities for radar echoes to bounce off clouds, terrain, and the spacecraft itself in complicated ways. If you can get clean, accurate maps out of that mess, doing radar work on airless or thin atmosphere bodies is much easier. Even for exoplanets, the experience matters. You don't get direct radar images of those worlds, but you do need to understand how surface roughness, rock type, and atmosphere interact, because those factors feed into how the planet reflects and emits light at different wavelengths. Venus gives you a real data-rich case, where you can tie surface physics, atmosphere, and observations together tightly. So with radar, you finally get to see the ground under permanent cloud in 3D and track changes down to centimeter scales. But there's still one more layer you can't skip over, because everything that radar reveals is sitting under an atmosphere full of complex chemistry. To really know whether that atmosphere is just hostile gas or something that once hosted, or maybe still hosts, any trace of biology, you have to stop guessing about what's in those clouds and start reading their chemistry directly, from top to bottom. Why do serious scientists even keep the life at Venus idea on the table when the surface can melt metal? The reason is that you have to stop thinking only about the ground. Around 50 kilometers up near the middle of the cloud deck, the pressure is close to 1 bar, like sea level on Earth, and the temperature sits in the rough range of 30 to 70 degrees Celsius, about 86 to 158 degrees Fahrenheit. That is hot and harsh, but it's at least in the general ballpark of environments where some Earth microbes can survive. The chemistry is brutal, the droplets are sulfuric acid, the air is almost pure CO2, but if Venus ever had life when it was cooler and wetter, this is the one region where that life could, in principle, have retreated and hung on as the surface went from bad to impossible. NASA is not sending DAVINCI or VERITAS to find life in the clouds. The instruments are not designed to shout yes biology or no biology. What they will do is nail down the chemistry and physics of those layers, so you can stop arguing from ignorance. Right now, people speculate about possible microbes in Venus's clouds using very incomplete data. After DAVINCI, the debate will at least be anchored to real, high-precision measurements instead of guesses and noisy old numbers. So what exactly are we going to measure? And how does that tell you whether anything strange is going on up there? DAVINCI's descent probe carries a mass spectrometer that will sample the atmosphere continuously from around 67 kilometers down to near the surface. It measures the main gases, like CO2 and nitrogen, but the real power is in the trace gases, sulfur dioxide, hydrogen chloride, hydrogen fluoride, and others at tiny concentrations. It's not just, is this gas present? It's how much, at what altitude, and how does that ratio change with height? Those ratios encode the balance between photochemistry driven by sunlight, volcanic outgassing from below, and mixing from winds and the convection. For example, sulfur dioxide gets broken apart by UV light higher up and can form sulfuric acid. Volcanic activity can pump fresh SO2 up from below. Hydrogen halides like HCl and HF relate to how volatiles move between the interior and atmosphere. If the vertical profiles of these gases match what you'd expect from known physical and chemical processes, the atmosphere looks comfortably normal even if it's extreme. If something looks badly off, levels that are too high or too low for any reasonable combination of volcanism and photochemistry, that's when people have to start asking whether we're missing some important abiotic process, or whether, in the very far background, biology could be one of the options. But bulk gas composition is only half the story. Life, if it ever existed there, wouldn't live in the atmosphere in general. It would live somewhere specific, probably inside the droplets themselves. Venus's clouds are made of sulfuric acid droplets, not water droplets, but they're not perfectly uniform. Each droplet can have slightly different acidity, different amounts of dissolved water, and different impurities. On Earth, in high-acid environments like some hot springs and mine drainages, we see extremophile microbes that tolerate very low pH and high temperatures, especially around 60 degrees Celsius. They often live in microenvironments, tiny pockets where conditions are just barely within their survival range. In Venus's clouds, the same idea applies, but with different chemistry. To test whether there are even any chemically plausible niches, you need to know the droplet size distribution, how fast droplets settle downward, how turbulence and vertical winds mix them, and how often they evaporate or grow. That's droplet physics, not sci-fi. If droplets fall too fast, any hypothetical microbe would be dragged down into hotter, deadlier layers before it could reproduce. If mixing is too violent, the environment may be too unstable for any complex chemistry to persist. DAVINCI's instruments, combined with cloud and wind data from orbiters, will help pin down those physical parameters. How big the droplets are at each height, how dense the cloud layers are, how the wind shear vehicle looks. Even if the final conclusion is no, the microenvironments are still too hostile for life, That is a real answer grounded in data, not a shrug. And while we're talking about life, there's a more subtle but very important reason to dissect Venus's atmosphere in detail, to stop fooling ourselves about biosignatures on exoplanets. Right now, a lot of popular talk around exoplanets goes, if we see oxygen, maybe that means life, or if we see certain sulfur compounds out of equilibrium, maybe that's biology. Venus is poised to wreck a lot of those simple assumptions, and that's good. If you look at Venus, you see complex chemistry driven by sunlight, high temperatures, and volcanism, producing gases and cloud patterns that can look weird without any biology at all. By mapping a purely abiotic sulfur-dominated atmosphere at high precision, seeing exactly how sulfur dioxide, sulfuric acid, chlorine, fluorine, and other species behave over different altitudes and times, NASA can clean up the list of what counts as a potential biosignature versus what is totally explainable by non-biological processes. That means fewer "we might have found life" headlines that evaporate when someone points out a volcanic explanation, and more robust criteria for saying, okay, this exoplanet really looks odd in a way we can't reproduce with known chemistry. This is where Venus plays an uncomfortable but crucial role. It's the no-life control experiment we've been missing. If DAVINCI and future missions come back with a very precise, very stable chemical picture of Venus's clouds and nothing in it requires biology to explain, that is not a disappointment. It's a win. It tells you what a super hot, high-pressure, sulfur-driven atmosphere looks like when biology is not messing with it. That becomes your baseline. When you look at an exoplanet spectrum that resembles Venus, you can say, this matches a lifeless Venus-style atmosphere. If something deviates from that in a way we can't model, then you have a candidate for something more interesting. In a universe where we are desperate not to be fooled by false positives, having one harsh, well-measured, apparently lifeless atmosphere as a reference is just as valuable as finding a world full of biology. Venus is that reference. It forces us to tighten our standards, to be honest about how weird abiotic chemistry can get, and to separate truly strange from just Venus-like. And once you accept that, the next step is even more uncomfortable, because Venus doesn't just tell you how life might fail to appear, it also shows you what can happen to a world's oceans and climate over billions of years. To understand how far along that path Earth might be, and how much time we really have before long-term changes in the Sun and our own emissions push us further toward that direction, you have to treat Venus as a kind of time machine for Earth's future, not just a hostile neighbour. The Sun is not stable in the long term, it is slowly turning up the brightness knob, and Earth is riding that curve whether humans exist or not. Stellar evolution is clear on this. Stars like the Sun get brighter by a few percent every 100 million years. That sounds tiny, but added up over 1 to 2 billion years, and the energy hitting Earth goes up enough to shift the whole climate system. Over those timescales, even with no human CO2, Earth's surface will tend to warm, ice will retreat, oceans will evaporate more, and the atmosphere will change. Push that far enough and you move toward conditions that in some ways look more like present-day Venus than today's Earth. Venus, sitting closer to the Sun and already past the runaway point, is like a preview of where inner rocky planets eventually go. It's a 1 to 2 billion year future Earth experiment that has already finished. So the real issue is not will things change, it's does Earth's climate system have strong enough brakes to slow or delay that slide for as long as possible? On Earth, a lot of long-term climate optimism is built on the carbonate-silicate cycle. In simple terms, CO2 in the air dissolves in rain, reacts with rocks, and gets carried to the oceans where it can end up as carbonate minerals. Plate tectonics then drags those carbonates down into the mantle and brings new volcanic CO2 up. That loop acts as a thermostat over tens of millions of years. If the planet warms, weathering speeds up and pulls more CO2 out. If it cools, weathering slows and CO2 builds up. Some models say that keeps climate roughly stable over billions of years. Venus is the counterexample sitting right next door. Same basic ingredients, no sign that climate stayed stable. Something in its version of that feedback broke. Maybe it stayed too hot for carbonates to form, Maybe it lacked the right kind of plate tectonics. Maybe water was lost too early for the cycle to work. Whatever the exact cause, Venus shows that stabilization is not guaranteed. Da Vinci's precise measurements of CO2, sulfur-bearing gases, and noble gases will let modelers run billion-year climate simulations with real boundary conditions instead of arbitrary guesses. If those models can match Venus's current state and its likely history, then we know which feedbacks fail and which survive as a star brightens. That connects directly to the question everyone really cares about. How long can a planet actually keep its oceans? Venus almost certainly started with far more water than it has now. The strong enrichment of deuterium compared to normal hydrogen, combined with thermal escape calculations, points to a history where huge amounts of water were broken apart by sunlight and lost to space. If you start with global oceans and end with a bone-dry surface and a thick CO2 atmosphere, at some point those oceans had to boil or slowly evaporate away. Measuring the exact current ratios of hydrogen to deuterium and the rate at which hydrogen is still escaping from the upper atmosphere nails down how fast that process happened. Was it a rapid early blow-off in a hot young solar system, or a slower drawn-out loss as the greenhouse effect intensified? Once you have that rate, you can plug it straight into how long can Earth keep liquid oceans type calculations. Earth is farther from the Sun and has a different atmosphere, so the numbers won't match 1-to-1, but Venus sets a hard example. Given enough energy and the wrong feedbacks, oceans are not permanent. They're a phase in a planet's life, and that phase can end. Then there's carbon, the backbone of climate control. On Earth, a lot of our long-term safety comes from the fact that carbon doesn't stay in the air forever. It gets locked into carbonate rocks, buried and subducted. That storage slows down big swings. On Venus, that storage seems to have failed or never really started. Temperatures are so high that carbonate minerals, if they try to form, can break down and release CO2 again. A different tectonic style, stagnant lid instead of active plate recycling, may mean carbon is not efficiently moved into the deep interior. The result is that most of the carbon stays upstairs in the atmosphere, where it drives the greenhouse effect instead of being stored as rock. Understanding exactly why carbon ended up in the sky instead of the crust on Venus tells you how delicate Earth's carbon sinks really are. Are we benefiting from a narrow range of conditions, right temperature, right water cycle, right tectonics, that make long-term carbonate formation and burial possible? Or could relatively modest changes in any of those factors have pushed us down a more Venus-like path? VERITAS's gravity and topography maps, combined with Da Vinci's chemistry, will help answer whether Venus ever had strong carbon sinks or whether its carbon was atmosphere-bound from early on. All of this rolls into the simplest, harshest statement about why NASA is going so hard at Venus. This planet is the worst-case climate walkthrough you can't do on Earth. On Earth, you cannot ethically or physically run an experiment where you push CO2 up until the oceans boil and the atmosphere thickens to tens of bars. You can only model those scenarios. On Venus, nature has already run a version of that experiment. Once you build a Venus climate model that matches reality from the upper atmosphere down to 93 bar at the surface, temperatures, winds, clouds, chemistry, everything, you have a fully constrained example of a runaway greenhouse end state. After that, when you take Earth-focused climate models and push them to extreme CO2 levels or high solar input, you're not just drawing scary cartoons, you're asking, so, does this pathway in the model start to look like Venus's path, and if so, how far along it are we? Every worst case you test becomes anchored to physics that has already played out one planet over. And that's the real tension Venus forces on you, because once you've seen the endpoint in detail, the next question is unavoidable. Given the sun's slow brightening and our own CO2 emissions on top of that, how much of our future climate is still under our control? And how much is simply a matter of how long we can delay sliding toward the same physical limits that Venus has already crossed? How do you know a planet has suddenly become important, not just to one space agency, but to almost everyone with a serious rocket? For a long time, Venus was basically on the bench. Then NASA greenlit VERITAS and DAVINCI, and almost immediately other agencies dropped their own Venus plans on the table. The European Space Agency is building Envision, another orbiter that will carry high-resolution radar and spectroscopy, plus a subsurface radar sounder that can probe hundreds of meters below the surface. India's ISRO has proposed Shukrayan-1, an orbiter with radar and a suite of spectrometers tuned for Venus's atmosphere and surface. In the span of roughly a decade, Venus went from the planet we kind of mapped once to a target that looks crowded on mission charts, with multiple orbiters and a descent probe all aiming at the same hell world. That pile-on is not random, it's tied directly to a shift in the science story around Venus. Several things happened at once. Reanalysis of Magellan data, with far better processing than we had in the 1990s, turned up evidence of huge lava tubes and possible volcanic changes over time. Venus Express reported time-variable sulfur dioxide in the upper atmosphere, and thermal anomalies that looked a lot like active volcanism. At the same time, exoplanet missions started finding more and more hot Earths and super-Earths right up against their stars, exactly the regime where Venus is the closest real example we have. Suddenly Venus stopped looking like an oddball neighbour and started looking like the prototype for a huge chunk of the exoplanet catalogue. When funding agencies see this one planet answers climate physics, planetary geology and exoplanet habitability all at once, they move. That's why NASA, ESA and ISRO are all stacking missions into the same 10 to 15 year window. They're not just chasing pretty pictures, they're trying to grab a once-per-generation chance to completely rewrite how we talk about rocky planets. So what happens when you treat Venus not as a flag-planting target, but as a coordinated system where every mission is a piece of the same puzzle? Start with VERITAS and Envision. VERITAS gives you global, high-resolution topography and radar imaging at tens of meters per pixel, plus gravity maps that probe the deep interior. Envision brings its own radar system, including subsurface sounding that can see down hundreds of meters, plus spectroscopy tuned to pick out rock and mineral types and to monitor the atmosphere. They overlap in capability, but they're not redundant. VERITAS gives you the big 3D shape and time-variable deformation. Envision dives into selected areas with different radar frequencies and viewing angles and can look for buried structures, old lava flows under younger ones, sediment layers, maybe even the internal structure of those gigantic lava tubes. Now plug DaVinci into that. DaVinci's one-shot descent gives you a precise vertical profile of pressure, temperature, winds, and chemistry, especially for gases like CO2, SO2 and noble gases. That data is the calibration point for all the atmospheric models that VERITAS, Envision, and any ISRO mission will use when they interpret their own spectroscopic and radar data. Shukrayan-1, if it flies as planned, adds more wavelengths and more observation geometries, catching the planet at different times, different angles, and different solar conditions. You end up with something that looks less like separate national projects and more like one giant multi-agency Venus observatory. One mission measures the air in exquisite detail along a single descent path. Others watch the entire planet breathe, flex, and radiate over years. Each mission fills blind spots left by the others. And here's the part that scientists care about maybe even more than the live mission years. The data will keep paying out long after the spacecraft are dead. Magellan wrapped up in the mid-1990s, and in 2026 we're still pulling brand new discoveries out of its radar files because our processing methods got better and our questions got sharper. That's with 120 to 300 meter resolution and limited coverage. Now imagine what happens when you have global 30 meter radar, centimeter scale deformation maps, detailed emissivity data, and fully sampled atmospheric profiles from DaVinci. You can reprocess that data with future algorithms, cross-match it with new models, and get answers to questions no one has even thought to ask yet. NASA and its partners know that. They're not just thinking, what can we publish in the first 5 years? They're thinking, what can we leave behind that scientists in 2050 and 2070 will still be mining for insights? Every bit of clean, well-calibrated data from Venus is a time capsule for future research. That time-delayed payoff is a big part of why it makes sense to go now, while our instruments and computing are good enough to build data sets that will stay valuable for decades. There's also a practical engineering side to this rush that has nothing to do with Venus specifically, and everything to do with how we'll explore harder targets later. Coordinating multiple missions to one hostile world is a rehearsal for even more ambitious campaigns. If we can line up an orbiter doing radar and gravity, another orbiter doing spectroscopy and subsurface sounding, and a descent probe that has to slam through 11 to 12 kilometers per second entry speeds and survive 90 plus bar and 460 plus degrees Celsius, all while sharing data and timing with international partners, then we can coordinate almost anything. Missions to Uranus and Neptune, complex fleets around icy moons, even far future interstellar probes. All of those will need tight collaboration and careful division of roles between agencies. Venus is the test. You've got harsh conditions, high-risk hardware, overlapping science goals, and different countries and Tessera all trying to squeeze the maximum information out of a narrow window of time. If we get that right here, at a planet next door, we prove we can handle it farther out where the stakes are higher and the light time delays are worse. And once you see Venus in that light, as a place where multiple space agencies are effectively building a shared long-term lab on top of a hell world, the next question gets sharper. If all of this effort is going into one planet, is it really just about Venus? Or is it because solving Venus is the missing step we need before we can honestly say where it makes sense to spend serious money next? On the Moon? On Mars? Or on something even stranger? Why does a planet that can literally crush and bake a spacecraft still look like a bargain? When you compare pure science per kilogram of hardware, from an orbital mechanics point of view, Venus is not the hard inner planet. To go from low Earth orbit onto a transfer path, the change in velocity you need to reach Venus is often slightly less than what you need for Mars. Launch windows come around more often, transit times are shorter, and you can chain in gravity assists if you want to get clever with energy. That means, for the same propellant budget, you can send more mass or more frequent missions to Venus than to Mars. Now, what do you get once you're there? With Venus, you don't just get another dusty, cold world to photograph. You get a full-scale lab for extreme climate physics, active or recently active geology, and direct exoplanet analogues. One mission can hit all of those at once: atmosphere, surface, interior, and exoplanet calibration. If you're measuring scientific return per kilogram of spacecraft launched, Venus is hard to beat. You spend one Mars-class budget and you get data that touches climate science, planetary formation, and exoplanet interpretation all in a single shot. And the environment itself is not redundant, it's a completely different part of the parameter space we barely know anything about. The Moon gives you something simple, vacuum and low gravity. Mars gives you thin cold air, lower gravity and dust. We have spent decades learning that regime. We know how rovers drive, how landers behave, how dust storms affect solar panels. Venus lives in the opposite corner. High gravity close to Earth's, extremely dense atmosphere, surface temperatures around 460 to 470 degrees Celsius, pressures above 90 bar. Each of those combinations, gravity plus pressure plus temperature, is a different regime of physics and engineering. We have good data for thin and cold. We do not have good data for thick and hot, where CO2 behaves differently, rocks react differently, and atmospheric circulation follows different patterns. Every time you leave that regime unexplored, you are making assumptions when you model exoplanets, gas giant moons with dense atmospheres, or even industrial environments on Earth. Venus fills that missing gap. Then there's the hardware side, which is not just a side benefit, it's a major motive. If you can build electronics, sensors, seals, and structures that survive even 1 hour in Venus's lower atmosphere, you automatically raise your game for everything else. You need high-temperature semiconductors that keep working where typical silicon electronics fail. You need cooling systems that can dump heat into an environment that's already at 460 degrees Celsius. You need insulations and coatings that hold up under high pressure and corrosive chemistry. Those technologies aren't for Venus only. They feed straight into missions to gas giants, where probes dive into deep, hot atmospheres. They feed into industrial systems on Earth that operate in furnaces, reactors, and high-pressure vessels. They even bleed into defense and aerospace tech where survivability under heat and stress matters. Venus is a hardware boot camp, a way of testing the edge of what we can build. Pass that test, and almost any other environment in the solar system looks easier by comparison. So why isn't Venus the centre of every space PR campaign? Why does Mars still dominate headlines and memes? Mars is easy to sell. It has red rocks, sunsets, rovers you can anthropomorphize, and a simple story about future bases and maybe even people. It lines up with colony fantasies. Venus doesn't give you that hook. No one is seriously planning a human surface base in 90 plus bar and 460 plus degrees Celsius. Venus sells something quieter but more powerful: paradigm shifts. On Venus, the payoffs are things like, we rewrote the habitable zone definition. We found the limits of long-term climate stability. We figured out how often Earth-like planets turn into Venus-like planets. And we mapped how active geology and atmosphere are tied together on a twin of Earth. NASA's core mandate is not to build colonies, it's to expand fundamental knowledge. If you weigh the hype value of more Mars selfies against the scientific impact of understanding runaway greenhouse physics, interior atmosphere coupling and exoplanet analogues, Venus starts to look like the scientifically responsible move. It is not as friendly, but it is more informative. There's also a simple narrative gap that Venus is uniquely positioned to close. We already have decent coverage of Mercury, a tiny hot rock close to the Sun with almost no atmosphere. We obviously know Earth in detail. We have strong data on Mars, a smaller world with a thin, cold atmosphere and a history of water. We've sent orbiters and probes to the gas giants and ice giants. What we don't have is a complete, modern, high-resolution picture of the one planet that should be our closest analogue. Venus, same basic size, similar mass, same formation neighbourhood. Without Venus, our solar system story has a huge hole in exactly the spot that matters most for understanding Earth-like planets in general. We're trying to tell a coherent story of rocky planet evolution with a Mercury on one side, Earth and Mars on the other, and a big blank where the most Earth-sized planet should be. Going back to Venus. With serious hardware and modern instruments, is about closing that hole so we stop pretending that a sample size of one Earth and one cold Mars is enough to explain every Earth-like world we're now finding around other stars. Once you accept that, the logic tightens. If Venus is cheaper to reach than Mars in many cases, if it provides a completely new regime of physics we barely understand, if it stress tests hardware in ways that unlock missions everywhere else, and if it fills the biggest hole in our solar system narrative, the question flips. It's no longer why go to Venus. It becomes how long can we pretend our picture of habitability is complete without fully understanding the one planet that looks most like Earth and ended up in hell anyway. And that's where all the threads you've seen so far pull together. Because once you fill that hole, once VERITAS and DAVINCI and the other missions have done their work, you're not just tweaking a few models, you're forced to rewrite what the word habitable even means, where the safe zone actually sits around a star, and how rare a long-term Earth outcome might be in a universe full of planets that look similar on paper, but may be much closer to Venus in reality. Those clean green habitable zone rings you see in textbooks are lying to you by leaving out the one planet that shreds the whole picture. In the basic version, you draw a star, you draw a green band around it, and you say, inside this zone liquid water can exist on a rocky planet's surface. In a lot of those older diagrams, both Earth and Venus sit inside or right on the inner edge of that green band. On paper, Venus is technically in the habitable zone, if you draw it lazily. In reality, you know what Venus is like now. Roughly 467 degrees Celsius at the surface, about 872 degrees Fahrenheit, 93 bar of pressure, almost pure CO2 zero liquid water. Calling that habitable is a joke. Once you fold in real Venus data, that green band doesn't stay simple. You have to include climate feedbacks that can run away, cloud behaviour that can either cool or heat, and long-term water loss driven by stellar radiation. When you do that honestly, the inner edge of the habitable zone moves outward, and it stops being a clean circle. It becomes a messy region that depends on a planet's atmosphere, rotation, interior heat, and history. Venus is the reason you can't get away with the cartoon anymore. So then you hit the next lazy shortcut we've been using for years, this idea that Earth-sized automatically means kind of like Earth. Look at exoplanet catalogues. They're filled with entries like radius 1.1 Earths, mass 0.9 Earths, rocky candidate. It's very tempting to slap the label Earth-like on those worlds and move on. But Venus is sitting there at about 0.95 Earth radii, with similar mass and density, and it absolutely does not behave like Earth. If you only knew its size and guessed from that, you would get the climate completely wrong. Without a Venus template, size alone is a trap. You'd look at a planet that's 12,000 kilometers in diameter, sitting just inside some model's habitable zone, and you'd say, maybe it has oceans and continents. Venus shows you that same size, same basic bulk composition, and a nearby orbit can instead give you a high-pressure CO2 furnace with no water, no plate tectonics, and no magnetosphere. NASA's Venus missions are the reality check here. They say, let's stop pretending radius and mass are enough information. To fix that, you have to change how you think about habitability altogether. You can't treat atmosphere, geology, and interior as separate boxes. Venus is the example that forces you to link everything. Interior heat flow controls volcanism. Volcanism releases gases like CO2 and sulfur dioxide. Those gases build the atmosphere, which sets the greenhouse effect and controls surface temperature. Surface temperature and the presence or absence of water then feed back into what kinds of rocks form, how they weather, and whether carbon gets locked away or stays in the air. On top of this, stellar radiation determines how fast water and light gases are lost to space. VERITAS plus DAVINCI are built to map that whole chain. VERITAS gives you gravity and topography, which tell you about the core, the mantle, and how thick and strong the crust is. Its radar shows you volcanic structures, rifts, and possible plate-like features. DAVINCI gives you the atmospheric chemistry and structure from the upper clouds down toward the surface, including noble gases that encode the planet's early history. Together they let you say, this interior structure leads to this style of volcanism, which leads to this atmosphere, which leads to this climate. Habitability stops being a one-parameter game and becomes a full system problem. And here's the uncomfortable possibility that drops out of that system view. Maybe Venus is not the weird one. Maybe we are. We like to think of Earth as a standard case, a normal outcome for an Earth-sized planet in the habitable zone. But if most Earth-sized planets near the inner edge of their star's habitable zone end up with strong greenhouse effects, no long-term carbon sinks, and no sustained plate tectonics, then the Venus outcome might actually be the rule, not the exception. In that scenario, a world that stays temperate with liquid oceans for billions of years, with active plate tectonics and a strong magnetic field, might be rare. You cannot test that idea by staring at exoplanets alone, because we don't have the detail for those worlds. You test it by fully understanding at least one Venus in depth. If, after VERITAS and DAVINCI, you can show that Venus followed a very generic path from hot early world to runaway greenhouse, and that path only depends on a few basic things like distance from the star and initial water content, then you have evidence that many inner edge planets out there will do the same. If, on the other hand, Venus turns out to be a total oddball with some bizarre internal quirk, then maybe Earth-like outcomes are more common. Either way, you only get a real answer by dissecting Venus, not by ignoring it. When you put all of this together, you can boil NASA's motive down to one hard, simple line. NASA is going to Venus because if you want to know how fragile Earth really is, how many Earth-sized planets are actually habitable and not just hot CO2 prisons, and what most rocky worlds near their stars actually become over billions of years, you have to stare straight at the twin that lost and measure everything it did wrong. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.